reputation as kind of approaching this as an academic frame set, simply because I got started in the whole password cracking thing through my research when I was getting my PhD. Uh, but I really do strongly believe in learning by doing. So I'm an active member in Team John Ripper, and I do participate in password cracking contests like, Crack Me If You Can, that's going on right now. Luckily, this talk is, being filmed, before the contest starts, so no spoilers here, unfortunately. But good luck to everyone else who's participating. So password cracking, really, it's my hobby and a little bit of an obsession, but it's not my day job, unfortunately. But my day job has been very exciting recently, though, because I really focus on medical device security. And you can imagine with all the craziness around COVID-19, that has been and it's been an interesting time. So one project that I really kind of want to highlight is the Open Ventilator Monitoring and Alerting project that I've been helping to contribute to. And there's actually a talk at the Biohacking Village this Sunday, and that I really highly recommend people go ahead and listen to. So our team members are giving it, and it really is going to talk to you about how the lessons learned and how other people can help contribute as well. Because this has been a big problem because, as I'm sure you're aware, there's been a huge demand for ventilators to be able to help deal with COVID-19. So there's been a lot of different projects that have kind of stood up to try to help produce, low-cost ventilators to help fill that need pretty quickly there. So rather than have every single do-it-yourself ventilator develop their kind of whole own monitoring and alerting framework, we're trying to produce one common one that can be applied to all these different projects across the board. So because when you have these ventilators being able to treating patients, the patients are highly infectious, so you don't want to have the nurses exposed to that. But if something goes wrong, you need seconds count, so you need to be able to forward all that sensing information that these ventilators are doing back to a centralized nursing workstation. And you need to do that securely because you're running this on a real hospital network. So that's been a really fulfilling project that I've been working on. So another thing that I'm kind of helping out with here, as I'll move my head, is I'm helping out run the DEF CON Biohacking Village's Capture the Flag contest. So this was originally supposed to be in Vegas. That changed, of course. So now a lot of medical equipment is actually sitting in my house. So I have to be able to provide a way for hackers from all over the world to be able to log in and hack these infusion pumps here without also hacking my smart thermostat. As part of that, I actually had to repurpose one of my password cracking rigs, as you can see there, in order to run all the VMs that are helping to keep people, on those ventilators and hacking those, and not, hacking my smart thermostat. So probably the first questions I should start kind of addressing here is, what does that PCFG stand for in, PCFG password cracking? So originally, well, I guess still technically, it stands for probabilistic context-free grammar, which is the kind of the modeling framework it uses in order to model how people create passwords. So if you're into, the serial-autonoma or, formal languages, this might actually mean something to you. But for most people, they hear that and they're like, oh God, that's like math and stuff like that. I mean, there's no way it's going to run on my computer. And then they just kind of like slowly walk away. So I decided it need to have a more descriptive name. So I went ahead and rebranded it the Pretty Cool Fuzzy Guesser. And this kind of explains it a little bit better about what it's actually doing underneath the hood, because you train this on a list of passwords, and then it'll go ahead and create guesses that are similar to those passwords, but different, which is really kind of important in order to help, expand your cracking session. Side note, this is my favorite slide I've ever made, so it's all downhill from here. So really kind of what it's doing is it's using machine learning in order to crack passwords. And when I say machine learning, I mean that in the traditional sense of a whole bunch of if-then statements. So it's not using neural networks or artificial intelligence, but you are training it on passwords that you expect to be somewhat similar to the target passwords that you're cracking. And when it processes that training password set, it extracts all sorts of probability information about the components of those passwords that it finds there. So it figures out things like, capitalization masks, whether numbers go at the beginning of the password versus the end, the probability of individual letters and numbers found in that password, keyboard walks, and so on. And so it goes ahead and creates a model based upon all those different types of probability information there, and then it uses those in order to generate very highly probable password guesses in probability order. So it'll start with the most probable password guess and go to the second most probable password guess and then go to the third one and so on until you crack the password that you're trying to find or you give up. So let me just move my signal here a little bit here. Uh, So just to kind of tie us back into probably what's going on right now, as I said, I don't know what the actual contest is going to be like for Crack Me If You Can, but CoreLogic helpfully provided a brief summary of what the scenario is going to be at least here. And so we're going to be targeting 12 different individuals, and those individuals change their passwords over time in order to be able to deal with more complex password creation requirements. And that sounds a little bit like something that PCFG might actually be useful for. So I'm really optimistic for this contest. You'll see how optimistic I am on Saturday when I'm actually we're giving this talk. But this is kind of the scenario that this was originally developed for in the first place. Of you know how a subject creates passwords, so you want to create passwords kind of similar to that, but you also want to go ahead and change them, and maybe for example, you use more complex rules or complex password creation requirements added on top of that there. So I'm available probably on Discord right now, and so I'll be able to answer questions about how potentially you might be able to tweak this in order to help in a scenario like this here. The fact that there's a lot of academic papers about this, though, is when I give a talk like this, I don't actually have to create any of my own graphs. I just can go to other papers there, look at the research that other people have done, and just pull out their graphs in order to be able to talk with it here. So one thing that I really kind of want to highlight, though, and you need to kind of look at this with a bit of a skeptical eye, is that you'll notice that all these cracking sessions are really, short. I know, 1 trillion guesses here. That might sound like a lot, but when you start talking about, GPU password cracking, you're talking about like under a second in order to generate all those. So that's just, no time whatsoever. And part of the reason for this here is that the PCFG approach, it's very slow. It doesn't, scale very well with multi-threading currently. So when you start talking about passwords that you want to be able to crack, it works very well when you're going ahead targeting very slow password hashes where you can only make thousands of guesses a second because the hash is very slow. But when you start talking about things like unsalted MD5, other attacks that are going to be much more effective because you can just make so many more guesses in the same time frame there. So when you start looking at faster password hashes, you can certainly go ahead and still use a PCFG to supplement your attack, and you can still go ahead and crack some passwords that you might not normally get. But in general, for the faster password hashes, you really are going to want to go ahead and use more traditional types of password cracking attacks in order to really make use of the hardware that you have available to you. So I want to talk about this graph kind of and really focus on it because this was a really neat study done by Carnegie Mellon University. And one of the problems when you do academic research, especially when you start talking about offensive tactics, is that the academics are running attacks themselves. So you're looking at how effective students are at cracking passwords versus someone professional potentially. So CMU, took the probably the most straightforward approach to be able to solve that problem was they went out and reached out to CoreLogic. You might have heard of them. They're running this, Password Village. They run the Crack Me If You Can competition. So when you're trying to find an expert, they're like, way up there. So they're a pretty good representation for that there. So what they did was they gave one of the CoreLogic engineers a password list. They asked them to crack it, and they recorded how many passwords they cracked over time. It was the number of guesses they made, and then they compared that against other cracking sessions as well. And one thing I'm really it makes me smile every time I see this here is that the PCFG did really well compared to the pros, which was CoreLogic, for that short cracking session. So when you start asking, like, can this represent, how a real professional password cracker, operates? The short answer is it certainly, appears to be able to do that there. So, full disclaimer, when you gave, CoreLogic had more time, they definitely performed way better. This is a logarithmic graph, so that's about 100 times more guesses. And also, I'll admit this wasn't fair to CoreLogic either, because that's not typically how people crack passwords in real life. There was that such a short cracking session. And when it is that short, usually it's against a really strong password hash, and you have a lot of time in order to really manually tweak your attack that you're running there. That being said, if any of you are listening, I would love to have a repeat or a rematch of this, attack, just to see, how this performs with all the new improvements that have been made into PCFGs, and I'm sure that CoreLogic has really been upping their game over the years as well. So that's why I'm somewhat hopeful that we'll be able to find it, useful in the contest that's going on right now. So enough about all the research side of that there. Let's talk about how to actually make use of this PCFG password cracker. So the first thing is you just go ahead and download it from the GitHub repo. And the requirements of it, I really have strived to make it as simple as possible. So you need to have Python 3, and that's it. So there's an optional caret Python module that can help during the training, and that's because it helps detect what character encoding the training set is, because character encoding is the bane of my password cracking existence. But even that's optional, and actually it's now being installed as part of pip 3. So if you have pip, you probably don't even need to install it yourself as well. And this is really useful though, because I found a lot of situations where, like, when I'm cracking passwords, like I don't have like internet access, so it's really nice just to be able to go ahead and quickly just throw my tool on a box and get it to run. So if you can run Python 3 on the box, you can probably run this here. So I've tried it on a bunch of different OSs. I've actually even gotten it to run on NetBSD, and it was just pretty much the only thing I've ever gotten to be able to run on NetBSD. So hopefully this is easier than your typical academic tool set in order to be able to get it installed and start cracking passwords with as quickly as you can. So we start talking about hardware requirements, because that's always a important portion when we start talking about password cracking. Um, the PCFG toolset, it is single-threaded CPU bound, which is why it's so awfully slow. But it will use an entire CPU thread, so you do really need to dedicate one full CPU, thread to the PCFG. The other thing is it has very high RAM usage. It basically maintains a lot of different data structures in memory, and those data structures become more complex over time, so it just grows. So I could have done some things to try to go ahead and prune that, or move some of it to disk, but RAM is cheap, so I haven't. So it'll just keep on growing over time. So initially it starts out pretty low usage, but if you're talking about running this password cracking session for like a week or two, you really need to have at least 16 gigabits RAM to really kind of just fully dedicate to the PCFG toolset itself. So the next step is to actually make use of it and to run it. So I apologize up front that I tend to use the words rule set and grammar interchangeably, and at least to me they mean the exact same thing. But really what I'm talking about is that I mentioned machine learning a couple of times here. You have to go ahead and train a grammar on the existing password data set. Now, you may want to have, different grammars for different targets that you're trying to target. So if you're trying to target, a web application catering to younger people, you might want to train it on passwords that resemble that. If you're trying to target, corporate passwords, you might want to train it on corporate passwords instead. And then use those rule sets against target passwords that you're specifically, think will match that. So you can have as many rule sets as you want to be able to really kind of fine tune your cracking session there. So the default one rule set that comes with the PCFG password cracker was actually trained on a subset of the 1 million passwords from the RockU dataset, which came out in 2008, and it was against web passwords, so there wasn't really any strong password requirement whatsoever. I've been thinking about updating that, so if you have a good dataset that you think that I should use for that there, I'm open to hearing about that there to make it a little bit more effective. But that being said, the RockU dataset is still extremely effective even to this day. It's just, Blink-182 is not nearly as popular. So after you choose the dataset that you want to use, though, now you go ahead and start generating guesses. So it's a Python program, so you just go run Python 3. You run the PCFG guesser.py tool from the repo. You give it the name to rule set. By default, it's default. So if you don't go ahead and specify that there, it'll go ahead and use the RockU dataset. And then you go ahead and specify session name as well. By default, this is default as well. And so the session is used to restart a password cracking session. So if you have to cancel it for whatever reason, you can go ahead and restart it back up again. So I really want to kind of highlight, though, that the PCFG toolset is only a password guess generator toolset. It will generate password guesses. It will generate those password guesses in probability order. So it'll start with the most probable password guess, second most probable password guess, and keep on going down the line. It will not actually hash and crack any passwords. So you need to use another password cracking toolset for that there. Both John the Ripper and Hashcat work, or basically any other password cracking tool that accepts, guesses in from, the standard input there. As I mentioned earlier, I'm on Team John the Ripper, so I'm going to go ahead and use John the Ripper for pretty much all of my examples here, but you can totally use Hashcat as well. So in order to do this here, you run the previous command that I talked about, and then you run pipe it into, for example, John. And on John they have a command called standard in, so that you type that in there, and instead of running data from like a word list or generate your password guesses, it'll go ahead and use the password guesses that are piped into it instead. And you're cracking passwords. That's really all there is to it. So there's definitely optimizations for actually using this in the real world, though. So the first thing I really kind of want to highlight is a lot of times you want to know what the status of a cracking session is. So the challenge when you are using the pipe command, though, is if you go ahead and hit the enter button on your keyboard, instead of sending the enter button to John the Ripper, it's going to go ahead and forward that to my tool instead. So you might want to be able to, get John the Ripper to output a status report. So the way that you do that is you send a sig user 1 signal to John the Ripper. If you're writing this on a Linux system here, you just type in kill-sig user 1 and then the process identifier John the Ripper. And when you do that and you hit enter, it'll be just like hitting enter on the John the Ripper itself, and it'll go ahead and output the status output of its current cracking session. So now you can do things like, okay, not only see the passwords are getting cracked, but you can see like the number of hashes, the total number of hashes that are cracked so far. You can see like, for example, the guessing speed. So in this case, it's making about 4 million guesses a second. And then you can see like how long it's been running and, all the other, options as well. So I want to kind of dig into that one, output of that cracking session though, because I think, this really kind of helps demonstrate kind of some of the power of using the PCFG. Because normally when you're, this here is showing the passwords as they get cracked. So you can kind of see that it's not just going ahead and, figuring out one rule and then exhausting that rule and then going to the next rule like you would see in a more traditional password cracking session. Instead, it's creating much more fine-grained rules and iterating between all those depending on what the current probability of it is here. So when you see these passwords being cracked, it's kind of fun to try to figure out like how did the underlying system, generate that password guess? Why is it making the guess right now that it is? So kind of if you look up, initially here, like this is pretty easy. Okay, it's just taking like some 5-letter word. I apologize, my microphone just died here. So fun's doing DEF CON remote. So it's using 5 digits, or 5-letter words plus 4 digits here. Moving on, though, this is a kind of an interesting one here. Is Cess is cool. So I looked into my input dictionary, and Cess is cool was not in my input dictionary or my training set at all. And I found out that it was actually you doing multi-words for this here. So it was combining, Cess and then it's cool. So one kind of cool thing about this, and I'll talk about this a little bit later, is that instead of, going ahead and breaking this up into 3 words like we normally would think about it there, it actually broke it up into 2 different words. So Cess is cool. So that way you can go ahead and go through it and say like, okay, is, Katie cool? Is, Allie cool? Is, Bob cool? Because there's a lot of cool people out there. So it can go ahead and iterate through those there and try that type of, mangling rule for it there. And what's really cool about this is that that it learned that is cool is a common word from the training set itself. So I didn't actually ever program in that logic into it. It learned it by itself by looking at the training data, which is, as I said, pretty cool. But you can see after that there, it kind of went into brute force. It wasn't the pure brute force, and I'll talk about the different types of brute force here. It's actually combining just very short words, kind of like a combinator attack. But still, it's able to kind of get that out that way. And then it went ahead and tried, words with, special characters, the same special characters at the beginning and the end of them too. And that's, you might be able to see that in a traditional password cracking session, but you actually have to have a rule in order to generate that. And trying to create those rules is a real pain. So you won't see those in, most, common publicly available rule sets, but it was able to learn that from the training data, which was, I thought, pretty cool as well. So, down here, and I'm kind of, need to get off the screen here, but you can see it's trying some longer words, but these are actually, while they're normal words here, it's actually generated them via the multi-words as well. So like finger plus nail or 90 plus 9. And once again, this is kind of really useful because now you don't have to have things like 99, 98, 93, in your data set, your word list as well, because it's generating those on the fly. Kind of going down a little bit further here, this is your more traditional kind of rule here. It's just 2 digits plus capitalizing the first letter of a word. So you can see it's starting to do that. But settings is a pretty uncommon password word to be able to use. So it's trying it later in the Kraken session here. And now it's even combining even more mangling rules. So it's trying doing a multi-word, of wood plus fish and Terra plus dawn, and it's adding digits to the end of that as well. So you can see how it starts stacking these different rules together. And I kind of want to highlight that this cracking session has been going on, as you can kind of see from the stats output, for about 13 minutes. So all the really easy passwords have already been cracked. It's already guessed, 1, 2, 3, 4, 5, 6, and password 1, 2, 3, 4, 5, and so on. So these are starting to get into more of the, the fuzzier of the rule sets that you might not normally see in a normal password cracking session. So as I mentioned a little bit earlier, if you hit the enter button, it's going to go to my program, not John the Ripper. But there's a lot of information that I want to be able to provide to people about the status of your cracking session. So whenever you hit enter, or basically any of these R keys here, it'll display an output of what it's currently doing. So you can try to figure out whether you want to continue it, whether it's working correctly, and whether it's kind of doing what you want it to do as well. Kind of going through this here, I hit enter twice. And so you can kind of see how it's generating, these password guesses as it's doing it here. So the first one, it's, basically going ahead and trying to combine 2 words. So it's a multi-word type of attack. And you can, if you dig into like the real details of it there, you can kind of see that it's trying like the 143rd most probable word with no capitalization, and it's combining it to the 93rd most probable 4-letter word with no capitalization as well. So you can see that the probabilities it assigns to like even individual words and so that is very, very fine-grained. So it's going to try some words and then do other mangling rules and stuff like that, and it'll go back to the less probable words later on in the cracking session. So now this next one here, it's kind of a little bit, I'll try to get out of the way or something like that. You can see that it switched to a real brute force attack using Omen, or ordered Markov enumerators. And I'll talk about that a little bit later there. But really I kind of want to highlight though that it's trying, more traditional cracking rules. So it's like, combining words, and then it's switching to brute force, and then it'll switch to another mangling rule after this here. And then it'll just keep on going based upon whatever the current probability is. Now, as I said, I really struggle with documenting my code, so I try to go ahead and add as much documentation into the runtime behavior of it as possible. So if you, instead of hitting, enter or anything else along those lines, you hit H and hit enter, it'll provide, or just H actually, it'll provide a status report output of what all these different fields here mean. And that status report actually is much longer than even, displayed on the screen here. But it explains what all those different letters like A5 or C5 actually stand for. The one thing that I kind of really want to highlight though is this one metric here called probability coverage, because since the PCFG password cracker creates guesses in probability order, it starts with the very high probable passwords, and it goes to less probable passwords and less probable passwords. The model that it has will basically never finish. It'll just keep on figuring new combinations of words to go through to it. So a real challenge becomes, when do you go ahead and give up on a cracking session? So you haven't cracked a password. when should you go ahead and kill this off and try some other cracking type of attack that might be more successful, or when do you go ahead and just choose to say I'm not going to crack this password and move to a different case. So this probability coverage is a very fuzzy metric that I tried to develop to try to just give you a little bit of kind of a rule of thumb about when that should be. So what this metric says is that if the target password is the same probability distribution as the password data set that I trained, and if my grammar and how the model how these passwords are created was exactly correct, this is the probability that we crack this password. Now, these are one of those assumptions that's actually true in real life. The probability model the password you're trying to crack is probably very different. The grammar that I generate and train on is absolutely not perfect. But at least, as I said, it kind of gives you a rule of thumb to say, okay, this is starting to get a little bit high. It says, I had like a 90% chance of cracking this password. I haven't cracked this password yet. Maybe I should go ahead and give up. So, and you'll notice this number jumps up really high initially because it's making, high probability password guesses. And then it slows to a crawl to almost like no advancing after you get to, like 70 or 80, 90%, completion there. So this is kind of really good to be able to figure out, where can I go ahead and devote that, that one single CPU and that RAM to somewhere else there. So another usage tip I just kind of want to highlight is that sometimes the cracking dynamic when it comes to speed is completely reversed. So you might be trying to crack very, very computationally password hashes, expensive password hashes, or a lot of let's say salted hashes, in which case you're really only making, a couple guesses a second. Well, this generator is generating, let's say, between 100,000 and 4 million guesses a second. So it gets backlogged. And basically essentially freezes while it waits for it to be able to send more guesses to the password cracking program. So occasionally, if you hit enter, it won't actually display the status, or it'll take a while to display the status, and that's kind of usually what's happening. So if that's happening, and you're kind of curious whether the password cracking session's crashed or not, I recommend going back to earlier advice about sending a signal to, let's say, John the Ripper, and just seeing how that's doing there in order to make sure that your password cracking session is still running. So as I talked about, multi-word feature has probably been the biggest addition to the new 4.0 rewrite, and it has completely shocked me how effective this has been here. So I won't talk too much details about it, but the one thing I want to really kind of stress though is that it is not language specific at all. It learns all what constitutes a word from the training set that you're giving it there. So it'll pick up things like new band names or proper nouns that are really kind of hard to specify inside a language dictionary or whatever new Pokemon just came out. And it identifies patterns like, I love and stuff like that. So this is very useful for being able to, try to target new, password hashes. So it is, as I said, it's not language specific. It works best with, I would say, kind of like European English type languages. It really struggles still with some of the other languages like Mandarin, but that is something absolutely that I really want to focus on more going forward here. It's not perfect. It's definitely a work in progress. So there is a balance between, creating, false positives and the matches here. If you don't see some of the base words in the train set by themselves, it won't identify them. But it's something that is evolving, and part of the new pull request from that I just received from somebody else actually has some improvements to this here that I'm really excited about getting pushed into main. So one of the other big features that have been added recently here is OrderMarkov enumerator. And the whole reason why I talked about this is that a similar approach can be taken for pretty much anything. So if someone creates a better cracking attack or cracking mode, it can totally be incorporated into a PCFG style attack. I'll be a little bit like the Borg in that respect. But the real challenge is to be able to figure out how to assign a probability to a password guess. So if you can assign a probability to a password guess, I can probably incorporate it into a PCFG. So just kind of in the last little bit here, I really kind of want to highlight some additional tricks that are very useful when it comes to cracking passwords. So the first one here is this skip root flag in the PCFG. And basically what this does is disable omen guess generation. And that's not to say that omen guess generation is something that's bad to do. It certainly definitely helps increase the success of a password cracking session. But you can this is a way to paralyze your attack. So if you're having another system that's going ahead and really cranking through your brute force attack, you might want to go ahead and do all your brute force on that other system or on that other thread, and then run the PCFG guesser really just to focus on the word mangling rules instead. So in order to do that, all you need to do is just when you run it, just type in skip root. Another flag that's really kind of useful is the all lower flag. And what this means is it'll stop doing any sort of case mangling on the password guesses. Let me try to move my picture just a little bit here, just to make it easier to read. As I go back. I apologize. Ooh, okay. Uh, so, uh, a lot of times you may want to not go ahead and do case mangling inside of PCFG itself. And one reason might be that the hash that you're targeting is case insensitive, like landman. That's not probably the best example, though, because if you're cracking landman hashes, you're not using PCFG in order to do that there. You're just going ahead and brute forcing that sucker and taking it out that way. Whereas more likely, though, is that case mangling is very distinct for how people do it there. So if someone does a certain type of case mangling, they have a tendency to keep on using that strategy for all their other passwords. So when you start doing things like targeted password cracking, you may not want to go ahead and just go ahead and do what everyone does. You want to really make a really specific case mangling for that particular individual. And in that case, what the better way to do this is that John Ripper supports a really powerful feature called pipe. So what the pipe does is instead of just going ahead and taking the guesses in from standard input and running them as is, you can apply additional rules on top of that like you would do in a traditional password cracking dictionary type of attack. So you can specify your very specific, case mangling rules inside John Ripper's rule set, and then pipe, the lowercase password guesses right into John Ripper and have John Ripper capitalize it itself. And that can be very powerful when you have an idea of what type of case mangling you want to be able to target. So I of course moved it to the wrong portion here. Let me move my screen again here. I apologize. So upcoming improvements, as I mentioned, there was an amazing pull request that was submitted to me with a bunch of new features. I'm slowly incorporating them into the core, but I actually have the features available as their own kind of tool called segmenter.py, and by that I mean, and I apologize if I mispronounced the name because I've only seen it written, but Chunwan Wang submitted this here, and it's really impresses me there. So probably the biggest feature I'm really excited about is late speak replacement. This has been a feature that has been kind of my white whale as far as implementing, and it's just every single time I've gone through it, it's just not been very effective. But that's currently incorporated into this tool has called segmenter.py that's included in the repo. That will go ahead and try to parse that information out. So I'm looking at getting that incorporated into my core trainer and then getting that incorporated into password cracking sessions in order to be able to really target that there. He also improved some of the multi-word detection, so he made that better. And then he also has incorporated some new approaches into the password scorer, which is a different tool that you can go ahead and submit your password into the password scorer, and it'll tell you what the probability of your password is, which is kind of nice as well. So all credit goes to him for these. Really impressed with this here. And if anyone else is looking at helping out too, I'm all about that. So thank you very much once again for that there. Okay, so let me move my screen around again here. Okay, so the next thing I currently want to talk about here is the compile PCFG guesser. So I've been talking about the Python toolset all along right now. So the compile PCFG guesser is a completely different fork, and as you kind of get the name there, instead of being written in Python, it's written in compiled C code. It's a little bit harder to get actually installed and running simply because when you start talking about compiling your code, it runs great on my machine, but it has challenges elsewhere. I tried to go ahead and use the Hashcat build makefile for this. So if you can build Hashcat on your computer, you have at least a better chance of being able to go ahead and get this running as well. But if you have problems, please reach out to me on the GitLab or GitHub site, and I can try to help you fix those there. So I will say that the trainer portion, it will always be written in Python. I just like writing Python too much to change that over. So basically, you'll go ahead and create train rule sets with the Python trainer, but then copy them over to be used in the compiled version here. Also, the compiled version has a tendency to lag in features from the Python toolset because, once again, I like writing Python. I'm not the best C coder in the world. So basically, if I write a hello world program, it's going to have like 5 buffer overflows and a segfault. So take with that as what you will there. But I'm making this available. If someone wants to write a better one, I'm totally open to that as well. But it doesn't have save restore, it doesn't have stats outputs, and it has no open guest duration. So all that being said, why bother with this here? And really, at the end of the day, the main reason is it's about 20 times faster than the Python toolset. And I've always heard that, C code is faster than Python. But when I saw that, I was like, holy crap. So I will be upfront. I'm actually, even with all these limitations, when I'm cracking passwords, I'm using the compiled C version now much, much more often than I'm using the Python one there. So because that 20 speed improvement is hard to beat for most password cracking sessions. So now I'm going to talk real quick about training passwords. So I've been talking about this a lot here, and there's a lot of different reasons why you want to go ahead and create a new password training set there. So language is a huge one. You want to be able to train on passwords that are similar to the target that you're trying to target. And another big one is that corporate passwords are very, very different than you'll see from websites. And I'm sure you probably heard CoreLogic talk about this before. Yesterday. But that's something that is very evident. So if you're trying to target corporate passwords, you probably do want to go ahead and train on corporate passwords versus going ahead and training on passwords for some gaming website. So another reason to go ahead and train it though is if you're targeting a specific password creation policy, or which mangling rules your target prefers. So one way to be able to really target that there is to train only on passwords that match that training set there. And there's other things you can do, like the password the rules or the grammar that I generate. I made sure that I didn't include anything like a CRC check or any of those sanity checks into it there. So you can actually open up the files themselves, they're just text files, and start editing the probabilities of different things in them by hand too. So if you say like, oh, this is one word I really want to go ahead and make it like highly probable, but I don't want to go have to train on a whole new train set. You can just go ahead and open it up, put that word in there, give it whatever probability you want, and that will just be read in and used in your password cracking session there. So the other reason that train on a password train set there is it generates a bunch of information, extracts a lot of information from that password set. So it's really useful to be able to analyze a new dump that you have accessible to you there. So for example, it'll pull out like common emails, it'll pull out dates and websites, and try to help you figure out where did this password data set come from there. So the next question, of course, is where do you go ahead and get these password data sets from? And there's a lot of challenges with this too, because a lot of the data sets are not optimal when it comes to training on. So I don't know if you know of hashes.org, but it's a really great site for being able to download all these dumps as they come out here. So for example, let's say you want to go ahead and train on this data set here. I'm not going to try to pronounce the name of that site because I'm sure I'll just horribly mangle it there. But when I did some Googling about this site here, it was a site for new college students trying to find a job in China. So that's kind of an interesting data set there that you might want to be able to use in order to train for crack passwords here. So if you download something from like hashes.org, the first most important thing is select the plain option, plain text option to train your rule set on, because you don't want to include the hash part of your training set because then they'll think it's part of the password and just it goes poorly there. So one other thing I really kind of want to highlight here, and this is a feature that I'm hopeful to be able to get added to the PCFG toolset. But I was informed by the owner of the site here that they actually do some additional things for encoding non-UTF-8 characters that my trainer will not fully parse correctly. So that's something I need to add in too, so that it goes ahead and uses the correct character encoding for non-English passwords. So I just want to put that warning out too for trying to train this on things like Mandarin. But one problem with a lot of these dumps here is the first one is they don't contain duplicate guesses. So duplicate guesses are really important when it comes to trying to figure out what the probability of password is, because if you don't have duplicate guesses, 1, 2, 3, 4, 5, 6 looks like a very just random string. So that's useful, but I will say when you run longer cracking sessions with PCFGs, that lack of duplicates becomes less and less important because you've already exhausted all the really probable password guesses. The one issue though is that the omen portion really does struggle without the duplicates. So you might not want to go ahead and enable omen guessing if you train on a dataset that doesn't contain any duplicate guesses there. The other problem with these dumps is that they only contain the passwords that have been cracked. Basically you don't know or learn anything about the passwords that haven't been cracked. That's not a deal stopper, but just it's useful to keep that in mind there, that the crack percentage is going to be very useful when it comes to figuring out how good a data set is or to create a new rule set. So in order to train on a password data set there, it's a Python program once again. You just give the name of the rule set that you want to be able to train it on, as well as the password data set that you want to train it on as well. And they'll go ahead and run in order to do all the parsing and stemming of the password data set here. It will try to auto detect what that encoding is. But when in doubt, set it to be UTF-8 because the encoding really does matter quite a bit there. So the first pass it takes through the data set there, it learns all the character frequencies and base words for multi-word detection. So it actually makes a couple different passes through the same data set in order to learn more and more and more about it there. The second pass it goes through there, it'll do much of the real parsing of the password, so it figures out things like keyboard walks, alpha strings, letters, how probable like the digits are and stuff like that. So most of the stuff you think of traditionally when you talk about what the probabilities of different things are, it does on the second run through. And it actually goes ahead and makes a whole third run through then to see about how effective things like, Omen would be for cracking passwords. So that kind of gets back to how Omen generates the probability assigned with its different levels there. And so this takes a while. So if you're you're training it on 1 million passwords, it's done within like a minute or two. If you're training it on 1 billion passwords, it takes significantly longer. It has to keep all this data in memory. So if you're training on some of these really gigantic data sets there, it's just not going to work. One thing you might want to do is just select a subset of that password set, chosen randomly, in order to train your rule set on instead. So after you're all done with that, though, it'll display statistics about the data set you just trained upon, too, which are really kind of useful to figure out, where it came from. So, password lengths and stuff like that. But one thing that I've been kind of added that I found really useful is it'll display kind of like the top URLs, which are usually at the beginning, the top of them are like, web, email account information. But if you start getting down a little bit, you can actually see usually what the website is, because people have a tendency to use the website in their password. I also highlight the dates that it finds in there as well, because that's useful kind of trying to date when that password data set got leaked. Now, I want to kind of highlight that there's a long tail when it comes to the dates. I'm sorry, because people, create passwords before the password data set gets stolen. So you'll see a lot of passwords for years before the data set actually gets down. But if you start kind of going down it a little bit, you can say, okay, that's probably about where the cutoff was for when this password data set was disclosed. So kind of one last thing I really want to talk about real quick is that I am trying to get this to work with other cracking modes there. So one of the really popular cracking modes used is called Prince. Prince basically takes a lot of different words and just combines them all together and makes lots of guesses based upon that. But one challenge with Prince is that it's very dependent upon the input word list that you give it to it there, because the word list needs to have high quality words in it, but it also needs to have a level of kind of cruft in there too, because if you want to go ahead and, let's say, add the number one to the end of a word, you have one in your word list by itself. But the challenge is the larger your word list is, the more words it's trying to combine, and then it starts to have issues there as well. So we have all this probability information about how a password was generated. So maybe we can go ahead and use this to create very bespoke word lists for like a Prince style guessing session there. So I created another tool called Princeling that basically just does that there. It goes. I'm sorry, my microphone just went out again there. But yeah, so it creates a very high quality word list there, and does it automatically. Because one thing I like about Prince is it's the tool, the kind of the attack that I run when I want to goof off. So like password cracking sometimes it takes a lot of brain cells because you're kind of looking at how you're cracking, you're trying to optimize your cracking session. And Prince is like, I have no idea what I want to do. I want to go watch Tiger King on Netflix. Let's just go ahead and just launch this off and come back and see if it was successful. And Prince is usually actually quite successful. So it's a pretty good tool to be able to use. And by anything that you can do in order to automate Prince even more, I'm all for, which is why I went ahead and created that. So I'm going to go ahead and stop the live stream here, and hopefully I'll be on Discord there in order to answer any questions that you have. I hope you enjoyed this. I hope this was helpful. And once again, thank you for attending the Password Village here at DEF CON Safe Mode.